Hi, welcome to ERC Tipsnology. In this video, you will learn how to write an 8051 program using timer delays. First, let's talk about the time delay for different kinds of 8051 chips. There are two factors that can affect the accuracy of the delay. First of all, we have what we call as crystal frequency. The duration of the clock period of the machine cycle depends upon the crystal frequency. So this is considered first. Secondly, we have what we call as 8051 design because the original machine cycle duration was set at 12 clocks, and different advances or development in both IC technology and CPU design in the previous years or in the current years have made the one clock machine cycle a common feature. As you can see in this table, we have the clocks per machine cycle for different kinds of 8051 versions. On the first column is the chip maker, and on the second column are the clocks per machine cycle. For 8089C51 made by Atmel, the clocks per machine cycle is 12. This is what we normally use in our examples. For the other kind, which is done by Philips company, the P89C54X2, the clocks per machine cycle is equal to 6. On the other hand, for DS5000 by Dallas Semiconductors, it's 4. And for their other chips, which is the DS89C420 or 30, 40, or 50, this is the DS89C C4 series, it's equal to 1 clock per machine cycle. So this is important to consider in the delay calculation for 8051 microcontrollers. You have to know the clocks per machine cycle of the chip that you are making. I mean the chip that you are using. Now let's see this first example to find the period of the machine cycle represented as capital M and C for different kinds of 8051. But here we will assume that the crystal frequency is equal to 11.0592 megahertz. For letter A, 8089C51, we have 11.0592 megahertz divided by 12, and the answer would be 921.6 kilohertz. We need to divide the given value by 12 because for 8089C51, as we have mentioned before, the clocks per machine cycle for that chip or maker is 12, the 8089C51. That's why we need to divide it by 12. And that's how to find the frequency that is being asked in the problem. Now, if we want to take the period or we want to get the period, we know that the formula for period is equal to 1 over the frequency. So the microcontroller's period will be 1 divided by the frequency that we calculated, which is 921.6 kilohertz, and we will get an answer of 1.085 microsecond. If you want, you can also convert it to nanosecond by multiplying 1000, and it will be 1085 nanosecond. If you want it in second, then you have to divide this by 1 million, and it would be 0.000001085 second, because 1 second is equal to 1 million microsecond. Anyway, you can simply write 1.085 microsecond as the period for letter A, which is using 8089C51. For letter B, we are using P89C54X2 model or device. So as you can see here, with the clocks per machine cycle is 6. So we divide the 11.0592 megahertz by 6. We got 1.8432 megahertz. If you divide 1 over 1.8432 to get the period, we will get 0.5425 microsecond. For letter C, DS5000, you have to know the machine or the clocks per machine cycle of that chip. So that's equal to 4. So we have to divide our frequency, crystal frequency, to 11.0592 megahertz divided by 4, we will get 2.7648 megahertz. And dividing 1 by this answer, we will get 0.36 microsecond. So this is for DS5000 chip. And lastly, we have the DS89C4X0. This is 11.0592 megahertz divided by 1. We will get 11.0592 megahertz. And dividing 1 by this answer, we will be getting 0.0904 microsecond. So these examples, here we learned how to find the period, but before you can calculate for the period, we need to calculate first for the frequency. So we need to divide it by the given clocks per machine cycle. If it is not given, then you have to know the clocks per machine cycle first so that you can calculate for the frequency. And after that, just divide 1 by the frequency and you will be able to get the period. So this is how we calculate the frequency and how we calculate the period. Now, in the next slide, which is about programming timers still, so take note that the 8051 has two timers. And when we say timers, it doesn't really mean only as a timer, because the timers that we are talking about can work in two ways. It can be a timer or it can be a counter. So as a timer, it can be used to generate a time delay, like what we will do today, or as a counter or event counters, it can count events happening outside the microcontroller. So the timers can be used as a timer or as an event counter or simply counter. For timers of 8051, we have what we call as timer 0 and timer 1. And both of these timers are 16 bits wide. Now, for 8051 microcontroller, it's actually using 8-bit architecture, meaning that the registers that it is using is only up to 8 bits. And so because of that, the timer 0 or timer 1 needs 16 bits. We will have the situation where each 16 bits timer will be used or accessed as two separate registers. In other words, to be able to get 16 bits, we need two 8 bits registers. And we will call them as one byte will be called the low byte, and the other one byte will be called the high byte. Remember that one byte is equal to 8 bits. So as you can see here in this figure, we have D0, D1, D2 up to D15. So this is data 0 up to data 15. So all in all, we have 16 data. And data 0 to data 7, or this 8 data, will be called the lower byte for the timer 0. So we call it TL0, T for timer, L for low byte, and 0 to know that it's timer 0. And on the other hand, we have also what we call as TH0, T for timer, H for high byte, and 0 for timer 0. So from D0 to D15, this is what we call as the timer 0. But as I have said, timer 0 is divided into two parts. The low byte we called TL0, and the high byte, which we called as TH0. Same thing happens to timer 1, which is also 16 bits, but the 16 bits is divided into 8 bits TL1 and 8 bits of TH1. So again, TL1 means timer 1 low byte, and TH1 means timer 1 high byte. Same thing with TH0 and TL0. So as you can see here, timers 0 and 1 registers are accessed as low byte and high byte, and the low byte register is called the TL0 or TL1 for the timer 1, and TL0 for timer 0. And the high byte register is called the TH0 or TH1. And in assembly language, it is accessed or used like any other register. So if you want to put TL0 with a value of 4F hexadecimal number, this is the assembly language command. So it's equal to move TL0, comma, hashtag 4FH. So what will actually happen here, if this is C language, it's like TL0 equals 0x 4F semicolon. Now, on the second example here, we have move R5, comma, TH0. What will actually happen here is that TH0 value will go to register 5. So in C language, it's like R5 equals TH0. Moving on, both timer 0 and timer 1 use the same register which we call as timer mode or TMOD. And this is used to set the various timer operation modes. Talking about operation modes, we have mode 0, mode 1, mode 2, and mode 3. Now the TMOD or TMOD is an 8-bit register, and the lower 4 bits are for timer 0 and the upper 4 bits are for timer 1. And in both cases, the lower 2 bits are used to represent the timer mode. As you can see here, on the least significant bit M0, next to it is M1. So this M1 and M0 represents the mode for timer 0. And on the left side, we have M1, M0. This is for timer 1 to represent the mode for timer 1. So together, we will be having 8 bits from M0, M1, C, or T gate for timer 0 and M0, M1, C, or T gate for timer 1. Together, they will be equal to 8 bits. Now, the upper 2 bits will specify the operations. So this refers to the C slash T or C representing counter or timer and the gate. So again, this is what we call as the TMOD register. Now, for example, here the gate is the gating control, and when it is set or equal to 1, the timer or the counter will be enabled only while the interrupt X pin, the X here represents either interrupt 0 or interrupt 1, pin is high and the TRX control pin is set. So this can be TR0 or TR1. When cleared, the timer is enabled whenever the TRX control bit is set. So in other words, when the gate is 0, the timer is enabled whenever the TRX control bit is set. So the TR0 or TR1 must be equal to 1 aside from the gate being equal to 0. So just not to make you confused, just make gate equal to 0 if you are using the timer programming. Now, on the other hand, for C or T, this determines whether the timer will be used as a counter or as a timer. If you want to use it as a timer, then you have to put the timer or the C slash T value to 0. So we have to clear the C slash T or make this 0 so that we know that we will be using it as a timer. On the other hand, if you want to use it as a counter, then the C or T must be equal to 1. Again, if this is equal to 1, it will be used as a counter. If C or T equals to 0, then it will be used as a timer. And again, just to not make you confused, we will be using the timer programming using timers. So we will make C slash T also 0. In other words, gate is 0 and C slash T will be 0. Same thing with timer 0, gate will be 0 and C slash T must be made to be 0. So that's how we will make it as a timer. Now, for M1, M0 of timer 1 and M1, M0 of timer 0, this will determine the mode that you will be using. For example, if you make M1, M0 as 00, that means you will be using mode 0. If you want mode 1, then you have to make M1 0 and M0 1. So when we have 0 1 for M1, M0, that means it's mode 1. And if it is 10, that means it's mode 2. And if you want to use mode 3, that that means you have to put mode 1 as 1 and mode 0, or M1 as 1 and M0 as 1. So this M1, M0 can be 00 for mode 0, 01 for mode 1, 10 for mode 2, or 11 for mode 3. Same thing with timer 0. M1, M0 here can be 00 for mode 0, 01 for mode 1, 10 for mode 2, and 11 for mode 3. By the way, when you use mode 0, you will be operating as a 13-bit timer mode. It will be operated as a 13-bit timer mode. So important to remember these bits, 13 bits for mode 0, and 16-bit timer mode if it is mode 1. So remember the number, 16 bits for mode 1, 8 bits for mode 2, and split timer mode. Now, in the next slide, you will see here that we have an example where you need to tell whether the mode, what is the mode, and what is the timer that is selected for the following assembly language command. So if you have move TMOD hashtag 01H, what does it mean? Is it for timer 0? Is it for timer 1? What is the mode? So in the first question here, move TMOD, comma, hashtag 01H, the first number 0 represents timer 1, and the second number 1 represents timer 0. So it's always like that. For letter B, the number 2 represents timer 1, and the number 0 here represents timer 0. The number 1 here represents timer 1, and the number 2 represents timer 0. In other words, don't be confused. It's always like the first number beside the hashtag represents timer 1, and the second number here beside the H represents timer 0. So, by the way, these numbers are hexadecimal numbers as given here by the letter H. Therefore, it's one digit 0 here, but actually that's hexadecimal 0. So, it's in binary, it will be 0000. And then the number 1 here in binary will be 0001. In that case, then the timer 1 will be like 0 for the gate, 0 for the C or T, and 00 for M1, M0. And the 1 here, which is only 1, but it's actually 0001 in binary. And remember what we talked about, that the 0 will be for the gate, and then the next 0 will be for the C or T, which means it's a timer. And the last two bits will represent the mode. So in this example, the one here is represented by 0001. Therefore, 01, that means M1 is 0, M0 is 1. That's mode 1. So this is actually timer 0 mode 1. As you can see here, letter A, TMOD is equal to 0000 0001. It says this is mode 1 of timer 0. Actually, you can also say this is timer 1 mode 0 and timer 0 mode 1. But because the other one is all zeros, so we can just consider that we want to use timer 0 mode 1. For letter B, the number 20H is represented by 0010. Again, as a review, the first number is 0. It's represented by 8, so we don't need to add that. The second number 0 is 4, so it's also 0. The third number is 1, that's 2, and the fourth number 0, that's for 1. Therefore, this is equal to 2 in hexadecimal number. But in binary, 0010 is, that's the binary, and 2 is the hexa. And of course, the last number here is 0, hexa. So in binary, that's 4 zeros. I hope you understand that. In other words, actually, this is mode 1, sorry, mode timer 1, mode 2. And on the right, this four zeros is representing timer 0, mode 0. So if I want to write the complete answer for letter B, this is actually timer 1, mode 2, timer 0, mode 0. But because we don't really put anything on timer 0, so we just consider that this is timer 1, mode 2. We can say mode 2 of timer 1. We can also say timer 1, mode 2. Now for letter C, same thing, but for letter C, we have two numbers here. One, which is actually 0001, and two, which is 0010. So the number one in hexa is 0001 in binary, and the number two in hexa is 0010 in binary. So the two in hexa is 0010. As you can see here, timer 1, mode 1, and timer 0, mode 2. So that's the answer for letter C. Or you can say it in reverse, mode 2 of timer 0 and mode 1 of timer 1. So this is how to identify what is the timer and the mode that you are using given the assembly language program for TMOD. Later on, I will show you how to write that in C language. Now, in this example, we will find the timer's clock frequency and its period for different kinds of 8051 based system. And the crystal frequency used here is 11.0592 megahertz when C/T bit of TMOD is 0. Again, if the CT bit of TMOD is equal to 0, then we want to use the timer as a timer, not as a counter. Again, if you make CT or C or T equal to 1, it means you want to use the timer as a counter. And if it is equal to 0, it means that you want to use the timer as a timer. Because again, the timer can be used as a counter or as a timer. So as said here on the left side. So all you have to do is to divide 1 divided by 12 multiply by 11.0529. Actually, this is 0.0952, I think. So let's go back to the original sample here. So it's supposed to be 11.0592. All right, so this is 11.0592, and this is not actually 529. So there's a typographical error here. So this must be 11.0592. Okay, as just like what we used before in the example here. All right, this one, 11.0592. It's not 11.0592. Now, if it is really, I mean, this is really the required frequency, or this is the given frequency in the question or in the problem, then we will be calculating it similarly in the similar fashion, like we first divide the number 1 by 12 and then multiply it by 11.0592 or 529, whatever it is, and you will get 91.6 megahertz. And then from to get the period, we just divide the frequency that we calculated and we will get 1.085. Now considering that this is 1.085, if you will go back to our previous example before, the answer 1.085 microsecond will be possible only if we divide 11.0592. So in other words, this is a typographical error. This is 11.0592, not 29. Now in the next examples, we will be talking about the TMOD register gate. So timers of 8051 can do the starting and stopping by using software or hardware control. So by software, we can start and stop the timer when the gate is equal to zero. As we have talked about, we have here the gate. So this gate is zero. Okay. And when the gate is zero, the start and stop of the timer will be controlled by your program by changing the value of your timer start TR. So we have TR0 or TR1. All you have to do is to set it if you are using assembly. So it will be set B TR0 or set B TR1. And if you want to stop the timer, it will be clear or CLR TR0 or CLR TR1. But in C language, we just write TR0 equals 1 semicolon if you want to start the timer, or TR1 equals 1 semicolon to start the timer. If you want to stop the timer, TR0 equals 0 semicolon, or TR1 equals 0 semicolon. That's easier than assembly. Now, these instructions start and stop the timers as long as the gate is equal to zero in the TMOD register. In other words, if your gate here is not zero, you make it one, then this software way will not work. You cannot set the timer to zero or one to start or to stop it. So the hardware way of starting and stopping the timer by an external source will be done if you make the gate equal to 1. I hope that's clear. Again, to summarize this page, if the gate equals 1, you can start and stop the timer by an external source. But if the gate equals 0, you can start or stop the timer by software or by your program or by your instruction. Now, look at this example here. We find the value of TMOD if we want to program timer 0 in mode 2 using 8051 crystal for the clock source and use instruction to start and stop the timer. So here you will notice that it was like divided into two parts. The first part on the left, 0000, actually represents timer 1, and 0010 represents timer 0. So again, the left side represents timer 1, and the first zero here is the gate, the second zero is the C or T, and the last two zeros is the M1 or M0. So we can clearly see that M1 is 0 and M0 is 0. So this is mode 0. So this is timer 1, mode 0. On the right side, we have four digits 0010. This is like the gate is 0, the C or T is 0, and the M1, M0 is 10. So this 10 means this is mode 2. Now, if you forgot it, we can go back to the slide. You will see here 10 is mode 2. So if M1, M0 is 10, that's mode 2. And it's very clear here that the 10 here is mode 2. So again, to answer this question, this is like timer 1, mode 0, and timer 0, mode 2. Or we can just say that this, in general, this is timer 0, mode 2. Okay, so that's this page. Now, in mode 1 programming, what will actually happen are the following. So the following are the characteristics and operations of mode 1. First of all, it is a 16-bit timer, of course. Therefore, it allows the value 0000 up to FFFF to be loaded into the timer's register. Now, you might wonder why this is only four numbers and it's supposed to be 16, because these numbers are just hexadecimal numbers. Therefore, although you see here 0000, this is actually a single zero here. In binary is 0000. So there are four zeros of binary for a single zero of hexa. And if that's the case, so we have four zeros, that will be 16 zeros. So that's a very long set of numbers to write. Now, in the case of F, we know that hexadecimal F means 15. So 15 in binary is actually 1111. So one single F here means 1111 in binary. Now, We will just continue with this video in the next part because